In this ICFD++ example, we are going to demonstrate the steps to set up a supersonic reacting flow case using the new Integral Computational Multiphysics Advanced User Interface, or ICMP AUI. This example case emulates the experimental configuration studied by Burrows and Kirchhoff. The problem consists of a hydrogen jet forced into a supersonic airstream and is designed to introduce the user to setting up and running a chemical reaction model in CFD++. Before jumping into this example, I will briefly cover the new features and components of the ICFD++ AUI for our first-time users. For a more in-depth understanding of the ICMP AUI features that are common across all Metacomp software, you can click on the ICMP AUI demo link that will show up at the side of this video, or by referring to the ICMP AUI section of your ICFD++ documentation. The ICFD++ interface is composed of 5 items: the menu bar, where my mouse is currently hovering, the toolbar, which has shortcuts to some commonly used functions and controls, and the canvas, where the geometry or solution can be displayed. Also the notebook, which currently shows CFD++ setup information, and then the action panel, where much of the problem setup takes place. Within the notebook panel, ICFD++ shows an action tree, or a setup wizard, which can guide you step by step through the various parts of the problem setup. There are also one or more information trees. In this case, we see the groups and boundary families tree and the boundary conditions tree. Each item in the action tree or information tree has corresponding items that show up in the action panel. This is where the user is given specific choices about the problem setup based on information supplied in previous panels. All panels are dockable and resizable so the user can customize the interface. Next, I'll briefly cover the mouse controls. The mouse is used to control the view of the geometry in the mesh within the canvas. Holding down the left mouse button and moving the mouse up and down, or left and right, will rotate the geometry about its horizontal or vertical axes. Holding down the middle mouse button and moving the mouse up and down, left and right, allows you to translate the geometry up, down, left, or right. Holding down the right mouse button and moving the mouse left or right will rotate the geometry about the axis normal to the screen. And holding down the right mouse button and moving the mouse up or down will zoom the view in or out. Next, I will open up a new AUI and start the case setup from scratch. In Linux, you can launch the AUI by typing mcfd AUI in a command shell. The user interface will open and we will see the first item in the action panel. The first panel prompts us to choose a working directory. In Linux, the default directory location is where you launch the user interface. Next, I will press OK to choose the current working directory. At this point, we can select Yes to both analyze our grid and also read the BC family file. After loading the grid files into the AUI, information about the cell types, the number of cells, the number of cell groups, and the number and name of the BC selectors is displayed. Here we can press OK. Focusing our attention back to the left side of the screen, we see the next item in the action tree is the Cell Types and Volumes panel. This panel is automatically populated according to how the mesh files were interpreted. The user typically will not need to change these settings. The occasional exception would be if the user wants to change how ICFD++ responds to negative cell volumes or negative cell component volumes that are encountered in the mesh. Pressing OK. Next, we see the General Problem Definition action panel. Here we will solve a single-phase, multi-species reacting flow problem. This falls into the category of a general fluids problem. We will select this option. We will also choose No for using a problem setup wizard and press OK. Next, we see the CFD Problem Definition panel. Here we choose the following options. For fluid type, we will select gas. For species content, we'll select multi-species. For the flow speed, we'll select mostly above Mach 0.5. Both the viscous and turbulent flow options will be set to yes. The thermal non-equilibrium option, the radiative heat transfer option will both be set to no. We'll select yes for modeling reactions. And our simulation type will be steady state. So now we can press OK. Next we see the action panel where additional specifications can be included. In this case there won't be any, so we'll press OK. Next we see the equation properties panel. First we are allowed to select between different equations of state. Here we will select the ideal gas law. We will also choose the two-equation realizable K-epsilon turbulence model. And we can select No to define passive scalars. Then press OK. Next we see the physics source terms panel. This panel allows us to introduce various types of source term effects. We will choose No to these options and press OK. Next we see the reference quantities panel. Here we will elect to solve the case in dimensional mode using the International System of Units, or SI, and press OK. Next we see the fluid properties panel. The first option will allow us to read a species and reaction file. This option can be useful for cases involving chemical reactions such as this one, where manually selecting every species and every reaction along with all the terms in each rate expression can be somewhat tedious. The present example uses 9 species and 18 reactions. And to skip this step of entering these, you can select this option. If desired, you can choose to import the information from an existing species and reactions file. There's a species and reactions file named reactions.rea that's located in the tutorial solution directory for your convenience. For this example, we'll keep this option unchecked and we will walk through the setup of all the species and at least a few of the chemical reactions. The next option asks us for the number of temperature ranges to use for the species properties curve fits. We will keep the default setting of 2. The bottom section of this panel is used to declare the multiple species to be tracked in our system. We can press plus to add additional species that will be tracked. In this case we have a total of 9 species, and you will note that one of them will not be tracked directly. This will be treated as the hidden species. The hidden species will be entered in the lower window. The mass fraction of the hidden species is computed using the balance of all the other species. For the hidden species, the basic guideline here is to choose one of the most abundant species in the system. One typically wants to avoid choosing highly reactive radicals, which typically have low concentrations or short lifespans. Species participating in chain branching reactions, etc. should be avoided. We can specify each of the tracked species. In this case, hydrogen is the first species. So we can click the database option to display all the different species. So I've added 8 slots for the tracked species. Now I can start with the first species in the list, which is molecular hydrogen, and drag that over into the first slot. The next species is atomic hydrogen, and I'll do the same. The next species in the list is atomic oxygen, so I find that in the list and drag it to species number 3. The next species is molecular oxygen. That's species number 4. Next is H2O for species 5. Next is hydrogen peroxide, species 6. HO2, species 7. And for the last of the tracked species, hydroxyl radical. Finally, we need to specify the hidden species. In this case, the hidden species is nitrogen. We can keep the remainder of this panel in its default state and press OK. Next, we see the reaction controls panel. You can choose No in the first option. We will not activate any user-given subroutines. Next, choose Yes to activate the specified reactions. Often, when running a reacting flow case, the user will want to first run the simulation with the reactions disabled and then transition to a setup with reactions turned on. This option allows a smooth way to do this transition. Basically, one sets up the entire problem with all the species and all the reactions defined, but with this option temporarily set to no. The user can then simply do a restart with this option set to yes. In this case, we will have the reactions turned on from the beginning of the run. Choose yes to activate the Smart Integrator. This option will automatically choose the number of steps taken with the stiff source term integrator. In this case, an ignition source will not be needed, so choose no for this option. You can quickly look in the advanced settings and you will find that the user can select two different types of reaction simulation modes. We will run this case using both of these options. We will first choose the default fractional step method, then we will repeat the simulation using the CFL independent approach. This setting determines how the chemical source terms are treated by the solver. In the fractional step approach, a fully implicit, tightly coupled procedure is used to invert the source terms. This approach can give robust convergence and accurate results, provided that the grid is fine in the flame region. Or if the grid is not so fine, then a lower CFL number should be used. Reaction source terms can, however, become CFL dependent when adequate mesh resolution is not possible, and in such cases the CFL independent approach can be used. In this example, we will demonstrate solutions with both of these settings. So in this panel we can press OK. Next we will see the reaction definition panel. ICFD++ uses basic Arrhenius type expressions to model the reaction rates. We can press the plus to add our first reaction. For each reaction, the user will be prompted for the reactant and product species. Reactants are at the top panel, products are at the bottom panel, the molar coefficients and exponents, a frequency factor, temperature and pressure exponents, the activation energy, and third body efficiencies when appropriate. You will also see an option to allow only a forward or a reversible reaction. You can press the plus button to add more reactants or products, and then the X button to remove them. Next, we will enter the information for our first reaction. In this case, molecular hydrogen interacts with molecular oxygen and produces two hydroxyl radicals. So we can press the plus to add an additional reactant. The molar coefficients for molecular hydrogen is 1. In this case, the exponents will be kept the same as the molar coefficients, which is typical of most elementary reactions. For the first species, we'll select on the list molecular hydrogen. The next species, select molecular oxygen. For the products, select OH. We'll enter 2 for the molar coefficient and the exponent. We'll select yes to allow this reaction to be reversible. We'll enter a frequency factor. Set the temperature exponent to 0, the pressure exponent to 0, and specify an activation energy. In this case, we don't have a third body collider, so we'll leave all of our third body efficiencies set to 1. At this point, we can add our second reaction. In this case, we'll have two reactants. The first one will be molecular oxygen. With a molar coefficient of 1, and atomic hydrogen, also with a molar coefficient of 1. Again, we'll keep the exponents the same as the molar coefficients. We will have two products. The first will be OH. The second will be atomic oxygen, both with molar coefficients of 1. We'll enter a frequency factor. The temperature exponent is 0. Pressure exponent is 0. We'll enter the activation energy. keep the third body efficiencies as their default setting. At this point, I've entered 2 reactions, and we have several more reactions to go. And to speed things up, I'll show you how we can read in a reactions file. You can press the read button at the bottom of the action panel. You can search for the reactions file. In this case, we're looking for a .rea extension. Find that, press OK. And this will populate our reactions panel with the remaining reactions. Okay, at this point we've loaded the species and reactions file, and it's populated the remaining reactions in the reaction set. So on this panel, you can press OK. At this point we will see the initial conditions action tree panel. Here we will want to choose the option to initialize the entire domain. You can see that there's other initialization options. Initialization by boxes, cylinders, cell groups, cell ranges, etc. We will use a temperature-based initialization. We will need to press the green plus to add an information set. And we'll enter the following values. For pressure, 101,325. For the initial temperature, 1270 Kelvin. Initial U component of velocity is 1775.63. 0 for the Y and Z components of velocity. And then we'll wait to initialize our turbulence values. At the bottom of the panel, you'll see that we specify the initial mass fractions for the species. For these, we'll specify a mass fraction for oxygen of 0.258. For H2O, 0.256. Then the remainder will be lumped into the hidden species, which is nitrogen. Here we can press OK. At this point, we will see the boundary conditions action tree panel. The 2 inlets, the BC named upper and the BC named outlet, will all be set to open BC types. The BC named wall will be set to a wall. So we can zoom into our geometry to get a better view, and we can toggle on the mesh and off. And you can see in the notebook panel, we actually have options of highlighting the different boundary conditions so that we can easily identify them in our geometry. See that the hydrogen inlet is very small, and the outlet. So we can start the BC definition by dragging the inlet boundary to the open boundary condition type. For the inlet BC, we'll choose the inflow only option under the boundary condition subgroup. We will also choose to define the type of information using primitive variables. Here we will choose the supersonic inflow option with a specified temperature. In this case, we will reuse the information set that's already defined by our initial conditions. And we can press OK. Next, we'll drag the BC named wall to the wall BC type. Here we'll choose viscous with the wall function option. In this case, we'll define an isothermal wall. We'll define the wall temperature to be 300 degrees Kelvin. And then press OK. You'll note that in the notebook panel, the BCs with green check marks have already been defined. You can hover over these for a short summary of their conditions. The BCs yet to be defined have red X's. So next, we'll drag the boundary condition named upper into the open BC subgroup. For this BC, we'll choose outflow only. We will also deselect the option to impose a BC at this boundary, and then impose a supersonic outflow option. We will deselect the option to impose a BC at this boundary, and then choose the supersonic outflow option. Press OK. Next, we can drag the BC named Inlet H2 to the Open category. For the hydrogen inlet boundary, we will choose Inflow Only. We will also choose Primitive Variables, and we will keep the supersonic inflow with the specified temperature option. Here, we will create a new information set by pressing the green plus. Click on the new information set. Specify the following values. For pressure, again 101,325. Temperature, we set to 254 Kelvin. X velocity is 1224.02. Again, the turbulence quantities will wait to initialize toward the end of the setup. Finally, we'll set the hydrogen mass fraction to be 1.0. Then press OK. So we have one less boundary condition to set. For the outlet, again, we'll drag that over to the Open Boundary Condition category. For this BC, we'll choose Outflow Only. Again, we will deselect the option to impose a BC at this boundary, and then choose the Supersonic Outflow option. And press OK. This completes the setup of the boundary conditions. So in the Action Tree panel, we can press OK. Next, we see the Turbulence Control Action Tree panel. Here we can accept all the default settings by pressing OK. Next, we will see the Turbulence Initialization Action Tree panel. Here we will need to select the first information set corresponding to the initial condition in the main inlet. So we can right-click the first information set. At the top, we can choose Yes, since we know the turbulence length scale. Next, we can enter a free stream turbulence level of 0.02. And we can enter a turbulence length scale of 0.001 meters. Next, we can press Compute. And here we will see the computed values for the turbulent kinetic energy and the dissipation rate of turbulent kinetic energy, as well as the value for turbulent viscosity divided by the laminar viscosity. Pressing OK will accept these values and apply those to the boundary condition and the initial condition. We can press OK again to accept those values. We will next select the final information set corresponding to the hydrogen inlet. We can right-click on that. In the panel, we can enter a turbulence level of 0.02, a length scale of 0.001. Again, the velocity is automatically populated. We can press Compute. This shows the turbulence values for this boundary. Press OK to accept those values. This completes the turbulence initialization. Press OK. Next, we will see a panel prompting us to choose if we want help setting up the numerical options. We can select Yes here. The main inlet Mach number is about 2.5. The hydrogen jet Mach number is higher than this, so we can select mid-supersonic option for the flow regime. In the options below, we can choose the area in which assistance with the numerical settings are needed. We can select both the Riemann solver panel, the spatial discretization panel, the time integration panels. We can select all of these and press OK. Next, we will see the Riemann solver panel. We can accept the defaults that were given by the Help Set Numerics option by pressing OK. Next, we will see the simulation strategy panel. We need to choose No for a clean start. We will set the case to run for 3,000 steps. We will reduce the convergence criteria to 6 orders of magnitude. And then press OK. Next, we will see the time integration panel. We will slightly reduce the maximum CFL number from 20 to 10, since this case involves chemical reactions. You will see that the CFL number will be ramped from 1 to 10 over the first 100 steps of the simulation. We will increase the max CFL adjustment factor from 0.95 to 1.0. At this point, we can press OK in the time integration control panel. Next, we will see the spatial discretization panel. We can press OK to accept all the defaults. Next, we will see the neutral plot file options panel. We will want to be sure to choose to write out the species mass fraction for each of the species that are included in our simulation. We can select the species or volume fraction output option from the pull-down menu. Individually, we'll turn on the mass fraction reporting for each of our species. And press OK. At this point, you'll receive a prompt asking you if you want to copy your neutral plot file options file to your plot output options file. You can press OK. And then press OK to close the neutral plot output file options panel. The next item in the action panel allows the user to select the frequency of output for the neutral plot files and also the solution restart files. You can accept the defaults and press OK. At this point, we can elect to save the input file and run CFD++. The general recommendation is to run in double precision. In this case, we'll run on a single CPU and press OK.
Take a few seconds and then it'll pop up.
As you can see, the case is running and the log file is being written to the working directory. The case will write output and restart files to the working directory. For more information on post-processing this case, you can refer to the results section of this example. Thank you.